everyone. In this video, we're wrapping up chapter 21 on our alpha carbon chemistry. So we're just going to briefly cover one last reaction called the Robinson annulation, and then we'll just summarize all of the reactions we learned in this chapter. So we'll look at additions to the alpha carbon, and then also additions to our beta carbon. So just really quickly, this Robinson annulation is kind of combining two reactions we've already talked about. So this will combine Michael addition and Aldol condensation. So first we'll perform Michael addition, and then we'll follow that with Aldol condensation. And this is actually going to give us a ring structure. So this can be very, very useful, specifically for polycyclic compounds, so 2-ring systems or more, depending on what you're working with. So let's say that we're starting with our diketone here that we saw before, and we're going to react that with base, which will take one of our acidic alpha protons. All right, so we form our Michael donor, or doubly stabilized enolate. So now we can attack an alpha beta unsaturated ketone or aldehyde, depending on what you're doing. Now, because this is a Michael donor, will this attack carbon 2 or carbon 4? And here I'll label our atoms. So where would that Michael donor attack? Carbon 4, right? So stable nucleophiles attack carbon 4, and we end up forming the 1,4 addition product. All right, so let's show that. Okay, so now we've got our 2 ketones, and we're adding in our alpha beta unsaturated ketone, which will now be protonated in the next step to form an enol. Let's see. Oh, actually, you know what? Just to simplify this, I'm going to just show the oxygen reforming its double bond, and then I'll show the alkene protonating itself, just so we can kind of skip that tautomerization step between the enol and the ketone. That'll be easier. And you can always do that on a test. I'll know that you know what you're doing. Okay, so in this next step, we are going to add base, more base. So we'll have more hydroxide ions. And this is what's going to give us our aldol condensation reaction. So here, our hydroxide wants to form an enolate. And we're going to have a lot of different alpha carbons on this molecule because we have 3 different carbonyl groups. But most likely we'll end up taking an alpha proton from the very end of our molecule here. And that's going to form our enolate for this next step. All right, so in this next step, that enolate, so the negatively charged carbon, is now going to attack the carbonyl carbon, one of them. In this case, it'll probably position itself towards that bottom one the way we have it drawn. But in reality, it doesn't really matter which one it attacks. And that's going to give us a second ring system. All right. And if you can't quite see how this formed, let's number our carbons. 1, 2, 3, 4, 5, 6. All right. So this carbon here is 6. We've got 5, 4, 3, 2, 1. So carbon 1 doesn't have any other groups on it. Carbon 2 has that carbonyl group on it. And then let's see, carbons 5 and 6 are the ones that are connected to the original ring. And carbon 6 has a negatively charged oxygen now. So now we just have to protonate that negative oxygen. So we could use water. That formed in the last step. And that will give us an alcohol at carbon 6. All right, so now we just have to perform our condensation step, and that's just going to involve heat and more base. And that's just going to perform elimination across this highlighted bond. So now we have a double bond in that same position. So if you ever have to form a polycyclic molecule, you could potentially use this Robinson annulation reaction. Okay, now let's go on to synthesis strategies. So we're just going to summarize all of the reactions we've learned in this chapter. So let's say that you want to add something to the alpha carbon on your molecule. So for instance, maybe you have a ketone and you want to add something to its alpha carbon. Let's say you want to add a bromine. How would you do that? Do you remember the reaction or the reagents we would use? We would use acid and Br2. All right, what if you have a carboxylic acid and you want to add bromine to the alpha position? Which reagents would you use? So we would use Br2 and PBr3, so phosphorus tribromide, followed by water. Okay, so again, here we're just adding a halogen to the alpha position. Now, what about alkylation? What if we want to add an alkyl group to the alpha position? So let's say we're starting with an asymmetrical ketone. And we want to add our alkyl group to the more substituted alpha carbon on the right. How would we do that? So we'd probably want to use a small base so that it could access the alpha proton on the right. So we could use sodium hydride, and that would be followed by an alkyl halide. Now, what temperature would we perform this reaction at? Would it be really cold, or would it be more moderate? It would probably be moderate or hot temperatures, so we could just even write room temperature. That would be fine. What if we wanted to add our alkyl group to the other side, to our less substituted alpha carbon? Which reagents would we use, and what temperature would we use? So if we want to favor deprotonating one of the protons on the left-hand side, on that less substituted alpha carbon, we want a base that is pretty bulky, so we would probably want to use LDA. And the temperature would probably be really, really cold at like -78 degrees Celsius. And then again, we'd follow that with our alkyl halide. Okay. Now, what if we want to add an alkyl group to our, what if we want to add or turn an alkyl halide into a carboxylic acid? So this would technically be another way to add an alkyl group to a carboxylic acid. Oh, so let me draw what I'm talking about here. So we've got our carboxylic acid, we have our alpha carbon, and then this R group. So this would be Malonic ester synthesis. And remember, we would start with diethyl malonate. So if we're starting with diethyl malonate, and we're turning this into a carboxylic acid with an R group at the alpha position, which reagents would we use? This one's kind of tricky, so it's okay if you're a little confused. It's hard to explain. So remember, we first want to start with an alkoxide base that matches the ester leaving group. So for this one, we would use that ethoxide base. Then we would follow that with our alkyl halide. And finally, we'd use some acid and heat to get our carboxylic acid. Okay, and remember, this is also really similar to the acetoacetic ester synthesis. But instead of a carboxylic acid, we'd have a methyl ketone. So just keep that in mind. All right, now let's look at some beta functionalization. So how would we, for instance, add an R group to the fourth carbon on this conjugated system? Oh, I misnumbered these. 1, 2, 3, 4. There we go. So another way of saying this is we're adding an alkyl group to the beta carbon on our alpha beta unsaturated ketone. So which reagents do we use? So we'd probably want to use a Michael donor because we're trying to add something to the fourth carbon. And remember, one of our Michael donors is that Gilman reagent, that organocuprate. And then we also have that water addition at the end. So we can protonate our oxygen, turn it into an enol, and then it tautomerizes to a ketone. Okay, now what if we want to turn an aldehyde into a beta hydroxy aldehyde? So we're essentially adding an alcohol to this beta position. How do we do that? So we would use base and water. Now we can actually take that a step further. If we add heat to this beta hydroxy aldehyde, what do we end up with? An alpha beta unsaturated aldehyde in this case. But it could be a ketone if we started with a ketone. All right, what if we're starting with an ester and we want to add a ketone to the beta position? So this would be a beta keto ester. What reagents do we use? So we want to use an alkoxide base that matches the ester leaving group, and we'll just follow that with water. Okay, so that's pretty much all of the reactions. We did also talk about the stork-enamine synthesis and the Robinson annulation. Those are, a little more complex, but it's always good to know you have other options available for very specific reactions. So these are kind of the main reactions to know for this chapter. And I did post flashcards for this chapter, so if you want to download those and kind of fold them up into little flashcards, you can. Or you can just copy them onto some index cards if you prefer that. But if you have any questions about these reactions, just please message me or set up an office hour. And I will see you in the next video.